Yes, Kerry contacted me and asked me to talk about optimizing CO2 injection wells. And I think others on the committee did as well. And I said, well, I can talk about injection wells, but I'd like to talk about some other things to optimize as well. So it's a little bit more than just the wells, but it's all about pushing CO2 into rocks. And here is a subsurface specialist. She's really good at digging holes. And she's also very keen looking out for hazards, which is typically what a CO2 storage person has to do. Be good at the subsurface, but be aware of hazards. So we want to get as much CO2 as possible into the well at the lowest possible cost, correct? No, wrong. So first of all, the question is wrong. What you really want to do is you want to maximize the CO2 stored over the project lifetime and do it safely and effectively. And that way, your banker, Jan Erik, will want to invest in your project. Okay. And that to me is very important. And and I know Owen's very good at analogies. So if you're a rich Italian and you want to go and buy a Lamborghini, beautiful car, it can go at 250 kilometers per hour on a racing track or perhaps a German Autobahn. But mostly you're going to have to keep it under 130 in Italy and in towns under 50 and near schools even slower because there are safety limits, okay? And it's exactly the same with the CO2 injection. Well, you do not want to run your CO2 injection rate at full pelt. You want to run it safely at an acceptable rate. Before I go on to the injectivity part of this problem, I thought I would throw in this slide from paper that we're very proud of about this early discussion about how we're going to get to gigatons. And what we said is, well, don't speculate about storage resources. There are plenty. Think about how many wells you need. And what we did is we took all of the wells in the Norwegian continental shelf, which is the green dots, and we pretended that they were CO2 injection wells into the future. And we pretended that the Norwegian oil industry started in 2020, but it was a CO2 injection industry. And we do an empirical correlation between cumulative CO2 stored and injection wells needed. And we used empirical data. And the conclusion was we need 12,000 CO2 injection wells by 2050 to reach the 2-degree warming scenario. That is not a lot of wells. Every year, the petroleum industry drills about 50,000 wells. And the wells we need to get to the 2-degree scenario are quite small. The red dots is the gigaton storage. So if you want to get to 1 gigaton cumulative by 2050, those red dots are the number of wells you need to drill. And then per continent, I've got these numbers in here. Currently, we've drilled about 50, so we've started, but we need to scale up. Now, Daniel came along and told us that the European Union wants to store 0.45 gigatons by 2050, approximately. That's a good ambition. Well, I can tell you exactly how many wells you need to get there. It is not many. That's the gigaton wells, 20 by 2030, 60 by 2040, and 100 by 2050, and half of that to reach the European goals. So really, this is a very, very manageable problem. So that was an aside. So let's talk about CO2 injection wells. I'm not a reservoir engineer, but the injectivity of a CO2 injection well is a very, very simple equation. The flow rate divided by the pressure difference governs how the well performs. So the injectivity index, II, is the ratio of the flow rate to the pressure difference. It has got more complex terms in that equation, radial flow equation, a gradient in the well to cover the viscosity. This is well-known well engineering physics. But the key thing is you need a KH product, which is a permeability and a thickness, to deliver your well. And this is a KH plot. And in general, we know that to have a viable CO2 project, injection project, you need a Darcy meter cutoff. You need at least a Darcy meter. Ideally, you'd like 10 Darcy meters. And just to show you how that works, after many years at Sleipner, we had a KH of nearly 200 at Sleipner most of the time. And it's gone very well, no problems, apart from in the first year when there was collapse into the well. At Snøhvit, the little blue dot, 1.1 million tons was injected in the Snøhvit tube-borne formation. And they did have a problem. And that's summarized in here. They thought they would have 40 Darcy meters, which was plenty. But then geology was a surprise. Things didn't go as well planned, and they actually had 6. It was enough for the project to sort of limp on for the first 3 years, but then they had to change their injection plan. So, you can expect geological surprises. So if you think your reservoir is going to be 50 Darcy meters, factors could bring it down, and you need to have robustness to cope with that. And ideally, you want to be much higher. So that's how you build robustness in your project. Now, neither the Sleipner project or the Snowit project run at full capacity. They have got well injectivity that is sufficient for project operational changes. Okay, and I could show you that in more detail, but another day. The summary of the Snowit project, which we published a few years ago, is this is the bottom hole pressure estimated at the Snowit injection well. And initially, you had this high pressure fluctuation at point A, which was due to salt dropout in the near wellbore environment because Roland's very dry CO2 was coming into a very salty formation. Salt crystals dropped out, affected the injectivity, and the group had to do something about that. And they found a chemical treatment to solve that problem, and that's why that fluctuation stopped. And then they resumed the climbing pressure towards B, and that was a far field effect. That was geological barriers causing the problem. And then eventually they decided to recomplete the well at a shallower level, the Stur formation, which they have carried on with ever since. So it's just a very good learning on the sort of surprises you could expect. And the two surprises you can expect for a C2 injection well are near wellbore effects, including salt dropout, and fines migration, and some chemical reactions. So we do have to think about those to link to Roland's talk. And the far field geological barriers. Here is the injection well. They targeted a nice, good quality sand, but there were some barriers, geological barriers, further away that over time caused the pressure buildup, meaning they had to change injection. This is a map, okay? This is a seismic map of the geological target horizon, and these are faults, okay? So they correctly targeted a fault block. They didn't drill near the faults. They targeted a good quality sand, but they found out that these sedimentary barriers some distance away from the fault had an effect, okay? And what I say, and the reason why I call this slide geological surprises is every CO2 injector will have geological surprises. What you need to do is be robust. And that's why you don't want to drive at full rate. You want to have some flexibility on the rates you can cope with. So let me just show you how that works in the sort of injectivity plot. So these are plots of injection rate versus wellhead pressure. And this is for Snøhvit in that first part. The blue dots are what is happening in that first part. And you can see the trend means that if they ran the well at full rate, 80 tons per hour, then they would have hit the fracture pressure. So in that difficult period here, they had to keep the rates lower until they fixed the geochemical problem. And then they're into the good injectivity line, and then they can run the well up to full rate, okay? So that's the split between the near wellbore effect and the far field effect. And then you might ask, well, what happens if you do keep on pushing hard on the rocks and you hit the fracture pressure? Wouldn't that be terrible? Not necessarily. We've tried that, and it's called the Insala project. So if I show you the injectivity plot for the Insala project, this was a reservoir where matrix and fracture flow were expected to happen. And when you look at the flow rate plot in here, you see a flip over as you increase the flow rate. You turn onto this flatter line, which is the fracture flow period. And we published this analysis to show you can see that oscillation between matrix flow and fracture flow. Now, it turns out that the Insala project needed the fracture flow to get rid of the CO2, but the problem they had was they also intersected a fault, which then sort of grew and then eventually was a concern. It didn't cause leakage, but it was a concern leading to the eventual stopping of the project. When we look at that data for Insala, one thing we noticed is that that fracture pressure can be read off the pressure data. So you can actually use real-time pressure data to infer your fracture pressure. And that's a very useful feedback because you can never predict precisely the fracture pressure. But with this technique, you could actually monitor it live in situ. And we also observed that the fracture pressure is changing over time. That's the 172 to 176 bars, which could be a far field effect. The pressure is increasing somewhere else. Or it could actually be a rock property effect. We don't know because it's a very subtle effect. So that's a very quick story of injectivity management, okay? So what about the geomechanics? So the reason why you don't want to increase the pressure too far is you don't want the rock to fracture in an unacceptable way, cause earthquakes or leakage. So this is a very simple cartoon of what was going to happen. You're going to increase the pressure in your injection interval that will cause some strain in your system. And that strain might be acceptable, but you want to avoid unacceptable strain, which might be a fault, like a small fault moving. I've borrowed this from another paper by Victor Villarasa. We want to keep our operating pressure below that critical fault. And this is a bit like your Lamborghini example. You do not want to drive your pressures right up to failure. You want to keep them manageable. So what we're trying to do is keep the pressure in a manageable form. Now then there's the thermal stress, and this is very recent work because hot CO2 going into cool CO2 going into a hot rock formation, and at Snøhvit there's about a 50-degree temperature difference. It could cause thermal fractures, and that puts you on that vector up there. And that's another risk to be aware of. But at the Snøhvit project, they decided those thermal fractures, if they occurred, they would help injectivity, and they would not cause fracture of the caprock. So they could be beneficial. And then, since I've only got 5 minutes, I want to say 5 minutes on Owen's challenge of the sheep in the field. So when we think about the pressure limits to storage, so at Snøhvit we had some far field effects. There's three types of systems: fully open systems where there isn't a pressure barrier, closed systems which you don't really want, which have a very low storage efficiency, and then there's semi-closed systems. Now the Snøhvit tube-borne formation was a semi-closed system, and we learned how to handle it. Okay, and because I'm a geologist, the real world is comprised of semi-open and semi-closed systems. There's no such thing as a closed system, and there's no such thing as an open system. And to sort of illustrate this, we took this giant prospect called Smeaheia, which is a huge fault block with many, many subfaults. And we analyzed that in terms of semi-closed and semi-open faults. And I won't show you the analysis now, but we published it. But we showed that we could definitely get a gigaton of CO2 into this huge fault block, as long as we prioritize the larger fault blocks that had room for pressure dissipation. So there are fault blocks that are too small, but we focus on the big ones, and then it's okay. And Equinor is now maturing this site. So to finish up with, I wanted to tell you about the thing that was not CO2 injectivity that I want to optimize, because I don't think it's only about CO2 injection in the mobile phase. We have to think about all the trapping mechanisms. And really, what we want to do is maximize storage. I don't have time to talk about the dissolution, but this is one detailed model of the dissolution of CO2 in water at the Sleipner site that we published. And to put it in a very short way, we think about 20 to 30% of the CO2 in the long term will go into the water phase. Do you care? I care. That's a very significant fraction. Okay? Now, incidentally, that's not far off the prediction 30 years ago. Now, because we've got Sandra here in the audience, I wanted to link to the basalts. So I've got three trapping diagrams. On the left-hand side, you see the basalts. Published trapping diagram for CO2 injection in basalts in Iceland. Most of the CO2 is going into the mineral phase, some into the dissolved phase. On the right-hand side, you've got the classic Sally Benson IPCC diagram, which is what's supposed to happen, okay? Mostly mobile phase and slowly going into the residual and dissolved phase. But what happens in reality, okay? Actually, the right-hand side is quite like Sleipner. But the one I think is interesting is the one in the middle. There you have most of the CO2 in the residual phase, quite a lot in the dissolved phase, and not very much in the mobile phase after 10 or 15 years. That middle one is actually Northern Lights. They publish their data in Norwegian in their permit application, so it's public domain information. And they're injecting in a dipping aquifer. They don't have a structural closure. In the very, very long term, if the CO2 was to migrate out of here, it would end up under this structural closure. So the long-term structural closure is there, but I doubt it will ever be used because the CO2 won't get there. In 25 years of injection, they expect the CO2 to go about 8 kilometers up dip by the end of their project, and most of the CO2 will be residually trapped. And quite a lot will be in the dissolved phase. So if you design your project so that most of the CO2 is not mobile, that's the way to optimize the storage. That really reduces the risks of leakage. So it's time for me to summarize. So just a 4 points. Generally, you want to keep the bottom hole pressures well below the max and keep your injectivity, below your injectivity limits. Near wellbore fractures could be beneficial. They're not a disaster at all. And then we're going to anticipate or mitigate these far field pressure barriers by thinking about the problem and managing the injection. And it's not just the CO2 injection well we have to optimize. It's the whole storage effort, which is all phases of storage. Thank you very much.